1, 2, 3, come on!
Hello students! Welcome to Teacher Sally YouTube channel. This is Rosalie Custodio, your science teacher. Today we will continue our discussion. This is the part 2 of electron configuration. To understand more our lesson, please watch the part 1 of this video. You may click the link found in the description box below. So now, let's begin. Today, we will talk about electron configuration. At the end of our lesson, you should be able to write the electron configuration or distribution of an element and determine the pattern of filling the orbitals based on the given distribution. But before we proceed to our discussion, let's have a review. Jumbled letters or word. Study the unscrambled letters. A clue is given to help you rearrange it into a proper word. Number 1. Electrons occupy the orbitals of lowest energy first. Correct answer is up-bow principle. Number 2. To occupy the same orbital, two electrons must have opposite spins. That is, the electron spins must be paired. The correct answer is Pauli exclusion principle. Number 3, it states that electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. The correct answer is Hand's rule. Number 4, the electrons found in the outermost shell or level. The correct answer is valence electrons. And last, number 5, the ways in which electrons are arranged in various orbitals around the nuclei of atoms. And the correct answer is electron configurations. Let's find out more. Two notations of electron configurations are used to describe the electronic structure of an atom. And these are the standard notations and the shorthand notation. When assigning electrons to orbitals, we must follow a set of 3 rules: the up-bow principle, the Pauli exclusion principle, and the Hand's rule. To help you describe the appropriate notation for electron configuration, it is best to show you an example. For this example, we will use the iodine or the iodine atom. There are 2 ways in which the electron configuration can be written. We have the longhand or the standard configuration, and we have the shorthand or the condensed configuration. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5 as the longhand or standard configuration for iodine or iodine atom, and we have Kr 5s2, 4d10, 5p5 as the condensed or the shorthand configuration for iodine. In both of these types of notations, the order of the energy level must be written by increased energy, showing the number of electrons in each subshell as an exponent. In the short notation, you place bracket around the preceding noble gas element followed by the valence shell electron configuration. The periodic table shows the krypton or the Kr is the previous noble gas listed before the iodine or the iodine. The noble gas configuration encompasses the energy states lower than the valence shell electrons. Therefore, in this case, the electron configuration of krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Let's elaborate. Let's have the standard notation of fluorine. A special type of notation is used to write an atom's electron configuration. The notation describes the energy levels, orbitals, and the number of electrons in each. In this example, we have the principal energy level of 1 and 2. And we have the sublevels of S and P. And the number of electrons in the sublevel, so we have 2 plus 2 plus 5 equals 9. This time, let's find out how to write the electron configuration of an element. Writing out the electron configuration of an element shows how many electrons are in each sublevel. An easy way to remember the order in which sublevels are filled is to write them out in rows. Then draw arrows through each sublevel starting at the top right of each row. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 4f, and 5d. The electron configuration of an element shows which sublevels are occupied and how many electrons are in each level. For example, here is the electron configuration of sodium. So we have 2 electrons in the 1s sublevel, 2 electrons in the 2s sublevel, 6 electrons in the 2p sublevel, and 1 electron in the 3s sublevel. To calculate the electron configuration of an element, first write out the number of electrons it contains. Remember that the atomic number is equal to the number of electrons. So oxygen, for example, contains 8 electrons. Write out the first sublevel and completely fill it with the electrons if possible. Keep account on the number of electrons used. Remember that an S sublevel can contain a maximum of 2 electrons. Write out the second sublevel and fill it with the electrons if possible. Carry on filling the sublevels in order of increasing energy until no electrons remain. Remember that the P sublevel can contain a maximum of 6 electrons. So here is the electron configuration of oxygen: 1s2, 2s2, 2p4. Electron configuration of transition metals. Although the 3d sublevel is in a lower principal energy level than the 4s sublevel, it is actually higher in energy. This means that the 4s sublevel is filled before the 3d sublevel. For example, what is the electron structure of vanadium? First, count the number of electrons in atom. So we have 23. Next is fill the sublevels, remembering the 4s is filled before the 3d. So therefore, the electron configuration of vanadium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d3. This time, let's have a practice. Write the electron configuration of the following elements. Number 1, hydrogen. 2, helium. 3, lithium. 4, beryllium. 5, boron. 6, carbon. 7, nitrogen. 8, oxygen. 9, fluorine. And number 10, neon. Now you get a periodic table of elements. Find out how many electrons the atom has. On the periodic table, the atomic number is the number of protons of the atom, and thus equals the number of electrons in an atom with 0 charge. Determine how many electrons are in the atom. Next, arrange the energy levels according to increasing energy. Take note of the mnemonic for filling the orbitals. Put 1 electron into the highest energy orbital available, starting with 1s. Once you have put every electron into an orbital according to the order, write the electron configuration. Remember, only write the orbitals that contain the electrons, and then the sum of the superscript equals the atomic number. In the periodic patterns, the period number or the row number is the same with the energy level. So we have period 1, period 2, period 3, period 4, etc. And the group number or the column number is equal to the total valence electrons. So we have group 1, group 2, group 3, 4, 5, 6, 7, 8. Now let us try to answer the electron configuration of hydrogen and oxygen. We have 1 principal quantum number, s sublevel, and 1 electron. For hydrogen with 1 electron, in a 1s orbital, electron configuration is written 1s1. So 1 here is the energy level or the period number 1. S here is the sublevel, the S block, and the superscript 1 here is the group number. For oxygen with 2 electrons in 1s orbital, 2 electrons in 2s orbital, and 4 electrons in 2p orbitals, the electron configuration is 1s2, 2s2, 2p4. Note that the sum of the superscript equals the number of electrons in the atom. Now let's have the trick in writing electron configuration. Let's have an example in S block. So let's take lithium. So what's the electron configuration of lithium using the periodic table? So we have 1s1 hydrogen, 1s2 helium, 1s2, 2s1 is the electron configuration of lithium. Let's have an example in P block. So we have here fluorine. So the electron configuration of fluorine is 1s2, 2s2, 2p5. Now let's have an example in the D block. So we have iron. The electron configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 using a periodic table. So this is 1s1, 1s2. Come back around, 1s2, 2s1, 2s2. So 2p1, 2, 3, 4, 5, 6. Come back around to third energy level, 3s1, 3s2. Then 3p1, 2, 3, 4, 5, 6. And then to fourth energy level, 4s1, 4s2. And then D block, 1, 2, 3, 4, 5, and 6. So here's the iron. Now let's proceed to electron configuration of ions. When writing electron configuration of ions, it's important to add or subtract the appropriate number of electrons. For negative ions, add electrons. For positive ions, remove electron. The way we designate electronic configurations for cations and anions is essentially similar to that for the neutral atoms in their ground state. When you see an element or a compound with a plus or minus sign after it, that tells you that it is an ion. Cations have positive signs after them, and anions have negative sign. For non-transition metals, the sublevels are then filled as for atom. So let's have an example. What is the electron structure of oxygen 2-? First, count the number of electrons in an atom. So we have 8 electrons for oxygen. Then second, add or remove electrons due to charge. So we have 8 plus 2, and that is 10. And then third, fill sublevels as for uncharged atoms. So therefore, the electron configuration of oxygen is 1s2, 2s2, 2p6. When transition metals form ions, it is the 4s electrons that are removed before the 3d electrons. For example, what is the electron structure of Ni2+? Again, count the number of electrons in an atom. So we have 28. Second, fill sublevels, remembering 4s is filled before. So we have standard electron configuration of nickel as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Third, count number of electrons to be removed. So we're going to remove 2 electrons since the sign is positive. And then lastly, remove electrons starting with the 4s. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d8 as the electron configuration of Ni2+. Let's have another example. The electronic configuration of cations is assigned by removing electrons first in the outermost p orbital, followed by the s orbital, and finally the d orbitals, if any more electrons need to be removed. For instance, the ground state electronic configuration of calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The calcium ion, however, has 2 electrons less. Hence, the electron configuration for Ca2+ is 1s2, 2s2, 2p6, 3s2, 3p6. Since we need to take away the 2 electrons, we first remove the electrons from the outermost shell. In this case, all the 4p subshells are empty. Hence, we start by removing from the s orbital, which is the 4s orbital. The electron configuration for Ca2+ is the same as for argon, which has 18 electrons. Hence, we can say that both are isoelectronic. Now, the electronic configuration of anions is assigned by adding electrons according to Abel principle. So we add electrons to fill the outermost orbital that is occupied and then add more electrons to the next higher orbital. Now, the neutral atom, fluorine, for instance, has 17 electrons. So therefore, its ground state electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p5. Now, the chlorine ion, on the other hand, has additional electron for a total of 18 electrons since the sign here is negative. Following the Abel principle, the electron occupies the partially filled 3p subshell first, making the 3p orbital completely filled. Now, the electronic configuration for chlorine minus can be designated as 1s2, 2s2, 2p6, 3s2, 3p6. Again, the electron configuration for chloride ion is the same as that for Ca2+ and argon. Hence, they are isoelectronic to each other. Next is the shorthand notation. So we have the standard notation of fluorine and the shorthand notation of chlorine. Now, use the last noble gas that is located in the periodic table right before the element. Write the symbol of the noble gas in brackets and write the remaining configuration after the brackets. Another example is sodium. Recall the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. We can abbreviate the electron configuration by indicating the innermost electrons with the symbol of the preceding noble gas. The preceding noble gas with an atomic number less than the sodium is neon, or Ne. We rewrite the electron configuration as this. In the condensed electron configurations, neon completes the 2p subshell. Sodium marks the beginning of new row. So we write the condensed electron configuration for sodium as Ne3s1. Ne represents the electron configuration of neon. So this is the core electrons or electrons in noble gas. The 3s1 is the valence electrons or the electrons outside of noble gas. Next example is sulfur. So sulfur has 16 electrons. Its electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p4. Now, we can abbreviate the electron configuration by indicating the innermost electrons with the symbol of the preceding noble gas. The preceding noble gas with the atomic number less than the sulfur is neon. So we rewrite the condensed electron configuration of sulfur like this: Ne3s2, 3p4. You can obtain correct electron configuration for the elements up to vanadium, having atomic number 23, by following the Abel diagram for orbital filling. If you were to continue, however, you would assign chromium and copper the following incorrect configuration. Now, there are two main exceptions to electron configuration: the chromium and copper. In these cases, a completely full or half full D sublevel is more stable than a partially filled D sublevel. So an electron from the 4s orbital is excited and rises to a 3d orbital. Now, how the exceptions work? The Abel principle holds for almost all elements, especially within the lower atomic numbers. Exceptions are based on the fact that half-full or full shells or subshells are more stable than partially filled ones. When the difference in energy levels between the two subshells is small, an electron may transfer to the higher level shell to fill or half-fill it. The electron occupies the higher energy level shell in violation of the Abel principle because the atom is more stable that way. Full or half-full subshells are very stable and have a lower energy than they would otherwise have. For a few elements, the normal sequence of energy level is changed because of full or half-full subshells. For higher atomic number elements, the differences in the energy levels becomes very small, and the change due to filling a subshell is more common than lower atomic numbers. For example, ruthenium, rhodium, sulfur, and platinum are all exceptions to the above principle because of filled or half-filled subshells. In the lower atomic number, the difference in energy levels for the normal sequence of electron shells is larger and exceptions are not as common. Now, in the first 30 elements, only the copper atomic number 24 and the chromium atomic number 29 are exceptions to the above principle. Now, the actual electron configuration of chromium and copper are the following. So, we have AR 3D5 4s1 for chromium and AR 3D10 4s1 for copper. Now, take a look at the diagram. Notice that for chromium, an electron is borrowed from the 4s subshell to give a 3d subshell that is exactly half-filled. Chromium has 29 electrons with 18 in the lower shells and 11 left over. By the above principle, 2 should go into 4s and 9 into 3d. But 3d can hold 10 electrons, so only 1 goes into 4s to make it half full and 10 go into 5d to fill it. The above principle works almost all the time, but exceptions occur when subshells are half full or full. For copper, has 4s electron is borrowed to give completely 3d subshell. Now, some actual electron configurations differ from those assigned using the above principle because although half-filled sublevels are not as stable as filled sublevels, they are more stable than other configurations. Apparently, half-filled and filled subshells have special stability that makes such borrowing energetically favorable. This subtle but nevertheless important phenomenon affects not only the ground state configurations of atoms but also the relative stabilities of some of the ions formed by the transition elements. Let's dig in, write the electron configuration, and show its orbital diagram. So let's have phosphorus. Create the electron spin diagrams and electron configuration of phosphorus. Phosphorus has 15 electrons, so there is a maximum of 2 electrons per orbitals. Electrons do not pair up within an energy sublevel or orbitals of equal energy until each orbital already has 1 electron. Now use the above diagram to place electrons in the orbital with the lowest energy first. Continue placing electrons in each orbital with the next higher energy level. The electron configuration of phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. The superscripts add up to the number of electrons, which is 15. Now let's take the electron configuration of carbon. 2 electrons will pair up with the 1s orbital in the 2s orbital, and the remaining 2 electrons will be placed into the 2p orbitals. The correct orbital diagram obeying the Han's rule will note the 2p electrons to be unpaired in 2 of the 3 available orbitals, both with the spin up. Since electrons always occupy an empty orbital before they fill up, it would be incorrect to draw the 2p electrons in the same orbital, leaving open orbitals unfilled. So the last example is oxygen. The electron configuration of oxygen can be written as 1s2, 2s2, 2p4. The orbital diagram is drawn as follows. The first 2 electrons will pair up in the 1s orbital. The next 2 electrons will pair up in the 2s orbital. That leaves 4s electrons, which must be placed in the 2p orbitals. According to Han's rule, all orbitals will be singly occupied before any is doubly occupied. Therefore, 2p orbitals will each get 1 electron and we'll get 2 electrons. Hand's rule also tells us that all of the unpaired electrons must have the same spin. Keeping with convention, all of the unpaired electrons are drawn as spin up. Let's remember, to gain more understanding about the lesson, this activity is provided for you. Read and analyze them well so that you will arrive on the right answers. What's the key word? What's the correct definition of these key terms? How good is your knowledge of keywords relating to electron arrangement? So let's start. Number 1, what is the correct definition of principal quantum number? A. One of 7 main energy levels in an atom in which an electron may reside. B. The number n used to label the principal energy levels. Or letter C. The amount of energy required to remove the first electron from an atom. The correct answer is letter B. Next, number 2. What is the correct definition of upload principle? Letter A. Electrons occupy the lowest energy sublevel first. Letter B. Each orbital may hold a maximum of 2 electrons. Or letter C. Single electrons fill all empty orbitals within sublevel before they start to form pairs. The correct answer is letter A. Next, number 3. What is the correct definition of first ionization energy? A. Amount of energy required to remove all the electrons from 1 mole of gaseous atoms. B. Amount of energy required to remove 1 mole of electrons from a gaseous atom. Or letter C. Amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atom. Next, number 4. What is the correct definition of Pauli exclusion principle? A. The principle stating that each orbital may hold a maximum of 2 electrons. B. Electrons occupy the lowest energy sublevel first. Or C. Single electrons fill all empty orbitals within a sublevel before they start to form pairs. The correct answer is letter A. Number 5. What is the correct definition of principal energy level? Letter A. One of the 7 main energy levels in an atom in which an electron may reside. B. An energy level represented by letter S. Or letter C. The amount of energy required to remove the first electron from an atom. And the correct answer is letter A. Lastly is Hand's rule. Is it A. Each orbital may hold a maximum of 2 electrons? B. Electrons occupy the lowest energy sublevel first. Or letter C. Single electrons fill all empty orbitals within a sublevel before they start to form pairs. And the correct answer is letter C. Let's evaluate. To check your understanding, answer the following. Write your answer in your notebook. Are these statements true or false? Number 1. Lithium has the electron configuration 1s2, 2s1. 2. Sulfur has the electron configuration 1s2, 2s2, 2p4. 3. Cl- and Ar both have the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. 4. Aluminum has the electron configuration 1s2, 2s2, 2p6, 3s3. And number 5, F- and N3- both have the electron configuration of 1s2, 2s2, 2p6. You may pause the video to answer this. Now here's the answers. Number 1 is true, 2 is false, 3 is true, 4 is false, and number 5 is true. So that's the end of our lesson. I hope you learned something new today. Watch out for the next video lesson in science. Answer the questions and activities in your module appropriately. Don't forget to like, share, and subscribe. This has been your teacher, Rosalie Custodio, saying, learning science is fun, cool, and awesome. Until next time, students, thank you for watching and have a nice day.